There are a number of applications of Gauss law. We consider one of the application, which is spherical charge. We assume that the charge is uniformly distributed on the surface of this sphere, and the radius of the sphere is a. The the surface charge density of the source is known, which is represented by rho s. So rho s is the surface charge density is the charge per unit area. So we know that the surface area of the sphere is given by S, and S in this particular case is equal to 4 pi a square. So this is the surface area of the sphere. As the surface area of the sphere is known and the surface charge density of the source is known, we can calculate the total charge on the surface of the sphere, and the total charge on the surface of the sphere will be equal to rho s into 4 pi a square. So this is how we calculate the total charge on the surface of the sphere. Now what we do, we consider a point outside the source. So we consider a point which is located outside the source, and we want to find out the electric flux density or the electric field intensity at the given point. So we are interested in the electric flux density as well as electric field intensity of this particular point. So in order to calculate the electric flux density or the electric field intensity at this particular point, we consider a Gaussian surface. We consider a Gaussian surface for the application of Gauss law. And the Gaussian surface is in the form of a sphere of radius r. Okay, so we consider a Gaussian surface of radius r, and the entire source is located inside the Gaussian surface. So here is the Gaussian surface, which is in the form of a sphere of radius r, and here is the source, and you see the entire source is located inside the Gaussian surface, and we apply Gauss law according to we apply Gauss law. According to Gauss law, okay, we do not apply Gauss law over here. We assume that the source, the radius of the source is so small. You see the radius of the source is a, and we assume that the radius of the source is so small that the source almost behaves like a point charge. So if it almost behaves like a point charge, then the electric flux density at the given point due to a point charge will be equal to Q by 4 pi r square into AR. So this is how we calculate the electric flux density at the given point due to a point charge. We assume that the radius of the source is so small that the source almost behaves like a point charge. So we apply this particular equation. Now we know that the total charge on the surface of the source will be equal to rho s into 4 pi a square. So we put the value of the charge in this particular equation, and we put the value of the charge in this particular equation. We put the value of the charge in this particular equation. So the electric flux density will be equal to rho s 4 pi a square divided by 4 pi r square into AR. We simplify the given equation, and here is the electric flux density at the given point. So the electric flux density at point P will be equal to rho s a square by r square into AR. So we will use this particular equation to find out the electric flux density at a point which is located outside the source. Now we consider another point which is located inside the source. Let's say here is point P, and the radial distance between this point and the center of the source is r. So in order to calculate the electric flux density at this particular point, we consider a Gaussian surface in the form of a sphere of radius r, right? And you see there is no charge inside the Gaussian surface. There is no charge inside this closed surface. You see the charge is located outside the Gaussian surface. So this is basically the Gaussian surface. So we apply Gauss law over here. According to Gauss law, the electric flux passing through the Gaussian surface in the outward direction will be equal to the charge enclosed by the closed surface, and the charge enclosed by the Gaussian surface is 0. So it means that the electric flux passing through the Gaussian surface in the outward direction will be equal to 0, and this implies that the electric field intensity as well as the electric flux density at this point will be equal to 0. So there will be no field inside the source, and there will be a field outside the source. So you guys can find out the field outside the source with the help of this particular equation. Now we talk about the first equation of Maxwell. Let us talk about the first equation of Maxwell. So we assume that the charge is uniformly distributed in a volume. So here is a volume charge. We assume that the charge is uniformly distributed inside this volume, and the volume charge density of this particular source is known, which is rho v, and the volume of the small portion of the source is known, which is dV. So if the volume charge density is known, we can calculate the total charge inside this volume. So the total charge inside this volume will be equal to the integration of rho v dV. So equation number 51 is used to find out the charge inside, you see, this volume. Okay. Now what we do, we consider a Gaussian surface in the form of a sphere over here. So we consider this the outer sphere, which is basically the Gaussian surface. So we consider a Gaussian surface in the form of a sphere as shown in figure number 27, and you see the source is located inside the Gaussian surface. So we apply Gauss law. Gauss law states that the electric flux passing through the Gaussian surface in the outward direction will be equal to the charge enclosed by the Gaussian surface, and the charge enclosed by the Gaussian surface is the total charge of the source, so which is equal to the integration of rho v dV. So the closed surface integration of the electric flux density will be equal to the integration of rho v dV, and we apply divergence theorem over here. According to the divergence theorem, the closed surface integration of d dot ds will be equal to the divergence of d, the integration of the divergence of d into dv. So this is the divergence theorem, where del dot d is known as the divergence of this vector, and you guys can calculate the divergence of a vector in a rectangular coordinate system with the help of this particular equation. So this equation is used to calculate the divergence of a vector in a rectangular coordinate system. We partially differentiate the x component with respect to x, plus we partially differentiate the y component with respect to y, plus we partially differentiate the z component with respect to z. This is how we calculate the divergence of a vector quantity in the cylindrical coordinate system. So this equation is used to find out the divergence of a vector quantity in the cylindrical coordinate system. If you guys want to calculate the divergence of a vector in the spherical coordinate system, we use this particular equation. So you guys need to know how to calculate the divergence of a vector in the rectangular coordinate system, how to calculate the divergence of a vector in the spherical coordinate system. So we put the value in this particular equation. You see, we know that this integration can be replaced by this integration, and we put the value over here in equation number 53. If we put the value in equation number 53, we have the divergence of d in the integration of the divergence of d into dv, which is equal to the integration of rho v dv, and if we simplify this particular equation, we get the divergence of d, which is equal to rho v, and this equation is known as the first equation of Maxwell.